So this is a joint work with Rahu, in which we investigated learning and automatability, two important concepts in the theory of computing, which, however, appear a priori rather unrelated. And the goal of our work was to find a bridge between them. Okay, so before explaining what we did, let's introduce some basic notions. We will work with Boolean circuits built on logical connectives. And I will use this notation, circuit S, to denote the set of all circuits of size almost S with n inputs. Unfortunately, our understanding of circuit complexity is still very bad. We don't know how to prove even superlinear lower bounds for any explicit Boolean function. Ideally, we would like to understand what is the size of the optimal circuit computing a given Boolean function for any Boolean function, and even be able to construct such a circuit efficiently if possible. This brings us to the notion of learning, which formalizes a closely related task. Igor already introduced this notion, but I will go through it quickly. So we say that circuits of size S are learnable by randomized algorithm L over the uniform distribution up to error epsilon with confidence delta. If for each function f computable by circuits of size S, the probability that the learning algorithm L, given oracle access to the Boolean function f, outputs a circuit C which 1 minus epsilon approximates the Boolean function f is at least delta.
Yeah? I'm sorry, any chance you can speak a tad bit louder?
Okay, yeah, I will try.
Thank you.
So this model of learning is learning with membership queries, because the learning algorithm L can ask for values of the Boolean function f on any input of its own choice. This is not necessarily the most practical scenario. Sometimes you have access only to values of the target function on random inputs. But it is an interesting open question if theorems, which I will present today, can be extended to this setting. I also made here the restriction that I consider only learning over the uniform distribution. It has been shown recently by Benedict, Karmozino, Kolokolova, and Ramaya and Sabin, right? That if you want to learn polynomial size circuits over other distributions, like polynomially sampleable distributions, you can reduce this task to learning polynomial size circuits over uniform distributions. So this restriction is not so substantial. The big question we can ask now is whether p-poly is learnable efficiently. And here I am abusing notation slightly. By p-poly, I mean circuits of size n to the k. So you fix the constant k, you look at the circuits of size n to the k, and you ask the question whether you can learn efficiently p-poly, this set circuits of size n to the k. This is a hard problem, but we can approach it by relating it to other standard questions in complexity theory. It can be shown that if p equals np, then p-poly is learnable efficiently, but the opposite implication is open. And we can ask also about the relation between learning and cryptography. It can be shown that if p-poly is learnable efficiently, then you can break all strong pseudorandom generators. But the opposite implication is again open. And if you could prove the opposite implication, this would establish a very fundamental dichotomy. It would mean that either strong pseudorandom generators exist and you can build theoretically safe cryptography, or efficient learning is possible. I will now switch to the notion of automatability, which formalizes proof search in propositional proof systems. So in order to define this notion, I need to introduce propositional proof systems, and I will do it just by giving a couple of examples. The most standard proof system for propositional logic is Frege system, which consists of finitely many derivation rules, which are sound and so-called implicationally complete, which essentially means that you can derive any tautology by combining these rules. And actually, it doesn't matter which finite set of sound and implicationally complete rules you take, because whenever you prove a formula tau in one Frege system, you can actually efficiently transform the proof into a proof in another Frege system, into a proof of the same formula in another Frege system. So we don't distinguish between Frege systems, and we speak about a single Frege system. Another natural proof system is extended Frege, which is defined in the same way as Frege system, but it operates with circuits instead of formulas. And we can see even very strong theories, such as set theory ZFC as propositional proof systems. ZFC proof of tautology tau is a proof which uses essentially any kind of mathematics which you can formalize in ZFC to derive that the formula tau is tautology. And there is an abstract notion of proof system, and it turns out that the question whether there is a proof system with polynomial size proofs of all tautologies is just NP versus QNP problem. So we can approach P versus NP problem by proving lower bounds on concrete proof systems like Frege, extended Frege, and ZFC. But right now, we don't know how to prove any non-trivial lower bound for Frege system. In proof complexity, we are not interested just in length of proofs. We also want to know how hard it is to find proofs. And this is formalized by the notion of automatability. So we say that a proof system P is automatable if there is an algorithm A such that for each tautology phi, the algorithm A given the formula phi finds a P proof of phi in polynomial time in the size of the shortest P proof of phi. So the important thing here to notice is that the algorithm A doesn't necessarily run in polynomial time. For example, if the formula phi doesn't have a short proof, if the shortest proof of formula phi in the proof system P is exponentially long, then the algorithm A can run exponentially long on the formula phi. It's easy to prove that P equals NP if and only if there is a proof system which is both automatable and which proves all tautologies efficiently by polynomial size proofs. So the notion of automatability is important, and the fundamental question we can ask is whether standard proof systems like Frege, extended Frege, and ZFC are automatable. Again, this is a very hard open problem. So at best, we can try to relate it to other standard questions. And again, it's very easy to see that if P equals NP, then you can automate all proof systems like Frege, extended Frege. But the opposite implication is open. It has been resolved recently in case of weak proof systems like resolution. But the question for strong proof systems remains completely open. Regarding the connection between automatability and cryptography, we know that if you can automate standard systems like ZFC, then you can break specific cryptographic assumptions, like the security of RSA. But it is not known how to break a generic cryptographic assumption, like the existence of strong pseudorandom generators, let alone to prove the equivalence between such notions. You see now that our understanding of learning and automatability is relatively similar. So with Rahu, we were interested in the question whether we can find a connection or stronger connection between learning and automatability. And an ideal connection between learning and automatability would say that for each standard proof system P, P is automatable if and only if P poly is learnable efficiently. Now with Rahu, we can derive the following version of this equivalence. We can show that for standard proof systems P proves efficiently that P is automatable on tautologies encoding circular lower bounds, if and only if P proves efficiently that P poly is learnable efficiently. And this equivalence holds under the assumption that the proof system P is sufficiently strong in the sense that it proves some circular lower bound, and it simulates so-called weak pigeonhole principle Frege system, WF. I will explain what this means in a moment. Let me just mention that this theorem differs from the ideal version of the equivalence in three main points. Firstly, we need to restrict the notion of automatability so that we consider automatability only on tautologies encoding circular lower bounds. The second thing is that we don't actually prove equivalence between automatability and learning. We prove the equivalence between provable automatability and provable learning. And finally, we need our proof system to be sufficiently strong. Perhaps the most remarkable aspect of this...
Is there a clear way to say what tautologies encode circuit lower bounds?
Yeah, I will speak those. I will explain. So probably the most remarkable aspect of this theorem is this unusual usage of metamathematics. I should say that I personally don't see it as a big deviation from the ideal form of equivalence, because it would be very strange and surprising if, for example, we had an efficient algorithm for p-poly, but we couldn't prove it in any standard proof system. So I will now proceed with a more detailed explanation of the theorem, and in order to do so, I need to define these formulas encoding circuit lower bounds. So I will denote by TTFS a propositional formula with the following property. The formula is tautological if and only if there is no circuit of size S which computes Boolean function f with n inputs. And the function f is represented by its truth table. So given a truth table of a Boolean function, the statement that there is no circuit of size S which computes the function f is a co-NP statement. So we can write down a propositional formula which has this property. And the formula is going to have size exponential in n, because it's going to use the whole truth table of the function f. This is going to be a hardwired string inside the formula. The formula will have polynomially many in S essential variables, which will stand for potential circuits of size S. So the formula will say that whenever you assign these variables by some assignment, the assignment either doesn't encode the proper circuit of size S, or the circuit fails to compute the function f on some input. We can similarly encode average case lower bounds, and I will use this notation TTFST to denote the statement that there is no circuit of size S which computes function f on at least phi minus t fraction of inputs. And we can now formulate our theorem in more detail as follows. So assume that a proof system P, so-called APC1, provably P simulates WF. I will explain what this means in a moment. Moreover, assume in addition that there is a Boolean function h such that the proof system P proves efficiently that h is very hard on average. Specifically, it proves that for each circuit of size 2 to the n over 4, no circuit of size 2 to the n over 4 computes the function h on more than 1/2 plus 1 over 2 to the n over 4 many inputs. So this is a very strong average case lower bound. But let's assume that this is provable in the proof system P. Then the following two statements are equivalent. First, provable learning. So the proof system P proves efficiently that p-poly is learnable by sub-exponential size circuits over the uniform distribution up to some error with some confidence. And I will ignore these parameters because there are generic ways how to improve them. So I will speak just about learnability of p-poly. I haven't explained how to encode this statement that p-poly is learnable efficiently by propositional formulas. And this is not trivial because we need to say that some probability is high, that the learning algorithm succeeds with high probability, and the probability is counted over exponentially big set. The way we deal with that is that we use approximate counting based on Nissan Wittgenstein generators. And it turns out that with this notion, yes?
In the assumption of this theorem, what does it mean P efficiently proves?
So you have a proof of size 2 to the ON.
Oh, that's what I thought. Yeah.
Okay. So there is actually a very natural way how to formalize this notion of approximate counting in the proof system so that the proof system can reason very fluently about the notion of learning and prove standard theorems about it. The second statement is provable automatability. And this says that P proves efficiently that P is automatable by non-uniform circuits on propositional formulas TTF poly n. And in more detail, the statement that P is automatable says that you have a circuit with the property that for each, the circuit C is given a propositional formula TTF poly n, and given such a formula, it can find a proof of this formula in the proof system P, which is not much longer than the proof of a different formula, TTF expressing sub-exponential size average case lower bound for the function f. So this differs from the standard notion of automatability. but it still carries the original message of automatability.
So yeah, when you say these are equivalent, this is like a formal equivalence or modulo this variance, this weakening.
So this notion of
No,
automatability.
I'm talking about the equivalence. When you say, is it like a formal equivalence or
Yes.
Okay.
So this is essentially precise formulation of our main theorem. I should explain. No, there is a question.
So,
Uh, yeah, so the question is if this theorem can be generalized to weaker circuit classes. I guess that you want to, for example, have like AC0 here and AC0 here. I guess it should.
so there's like a, not quite a mismatch, but I mean the time or length bounds. In one case, it's like polynomial in the size of the truth table. In item 1, it's quasi-polynomial in the size of the truth table. And I guess in 2,
Yeah, so I didn't explain properly how to encode this, and then you will see. If I did it, you would see better what are the parameters here. But in this formula, you can actually have, in this statement, expressing that people is learnable efficiently, you can actually use the whole truth table of the function f, and so the size of this formula is very similar to the size of this formula. But the problem is that here you are counting actually probability over a set of size 2 to the poly n, and this is much bigger than 3n. I should say what the system WF is. This is a very natural strengthening of extended Frege by the so-called dual weak pigeonhole principle, which allows you to use formulas of the form that some string B is outside of the range of a generator, which maps strings of length n to strings of length m for m bigger than n. It turns out that using such formulas, you can actually develop a machinery of approximate counting inside the proof system. And there is a theory, APC1, which is a fragment of Peano arithmetic, which corresponds to this proof system WF in a precise sense. Standard proof systems such as ZFC or WF do APC1 provability simulate WF, so I suggest we actually ignore this first assumption. The main assumption of our theorem is the assumption that the proof system P proves efficiently some circuit lower bound, very strong circuit lower bound. So let's discuss briefly how plausible this assumption is. There is actually a conjecture of Rasborough which implies that under standard complexity theoretic hardness assumptions, propositional formulas TTF poly n are hard for Frege system for all functions f. And it is possible to consider extensions of this conjecture to stronger systems such as ZFC. So if such strengthenings of Rasborough's conjecture hold, then the main assumption of our theorem fails. But actually, we do not know how to prove Rasborough's conjecture under any standard or plausible complexity theoretic hardness assumption. And if you look at all existing circuit lower bounds for weak circuit classes, which we have right now, they are all provable efficiently already in extended Frege, and often below. It is possible, actually, that if a circuit lower bound holds, then it is efficiently provable in Frege system. If you think that the complexity lower bound holds, then it is natural to expect that it is actually provable in some natural proof system like extended Frege or ZFC. In fact, under standard complexity theoretic hardness assumptions, there is a proof system and a function h such that the proof system P proves that the function h is hard for sub-exponential size circuits on average. So under standard complexity theoretic hardness assumptions, the main assumption of our theorem holds.
Yeah, is that known for next, not in ACC 0?
Yeah, so this is an exception.
Oh.
We don't know, no one actually tried to formalize Ryan's lower bound. So we don't know.
But pretty much, but everything else.
Well, there are so many
Yeah,
lower bounds out
well,
there
well,
that I
yeah.
can't really say everything, but standard methods are doable easily in extended Frege.
What does this proof system look like?
Which one?
The one
This one. Oh, this is very artificial. It's like essentially WF plus truth table tautology, which is just hardwired to the proof system for the function which is assumed to exist. So you assume that the hard function exists, and you hardwire the tautology which encodes the statement that it's hard. I hope that this slide is not too confusing. The point here is just to clarify that the status of the main assumption of our theorem is very interesting. If you want to believe in Rasberow's conjecture and its strengthenings, then you should read our main theorem as a disjunction, which says that either Rasberow's conjecture holds or some interesting equivalence happens. One more remark which I have here is that if you assume that this assumption of our theorem holds for extended Frege, and actually it suffices that extended Frege proves a worst case lower bound for the function h, for some function h, then extended Frege simulates WF, and you can kind of forget about the difference between these systems. I will now proceed with an outline of the proof with some historical remarks so that you actually see how our theorem arises from previous work. We build on the work of Rasberow and Krajicek. In the 90s, Rasberow showed that you can use natural proofs to derive unprobability of strong circuit lower bounds in certain fragments of bounded arithmetic under the assumption that strong pseudo-random generators exist. And around this time, Krajicek developed the notion of feasible interpolation, and he reformulated Rasberow's result in this language. And what you see here is essentially this reformulation. So this statement says that if you have an automatable proof system which proves efficiently hardness of some Boolean function, then you can extract from it a p-poly natural proof useful against p-poly. Now, more recently, Karmozino, Impalazzo-Kamez, and Kolo-Kola showed how to turn natural proofs into learning algorithms. So a direct corollary of these two statements is that if you have a proof system which proves some circuit lower bound and which is automatable, then you have a learning algorithm. So this is almost what we want. What remains to show is the opposite implication. And this is the real problem here. We don't know how to prove that, how to automate any standard proof system, assuming just that you have an efficient learning algorithm. So the way we deal with it is that we introduce this extra mathematical level, and now I claim that if you assume in addition that the proof system P proves efficiently that p-poly is learnable, then you can conclude that proof system P proves that P is automatable on tautologies encoding circuit lower bounds. And the way you do it is by formalizing the following simple argument in the proof system P. So if you know that your learning algorithm works, that it learns correctly polynomial size circuits, and if you apply the learning algorithm on the function f, on some given function f, and the learning algorithm fails, it doesn't output a small circuit, then you know that the function must be hard. Okay, so if the learning algorithm learns polynomial size circuits, but it doesn't learn function f, then the function f must be hard. Moreover, we can go to the next level and formalize also the statement that if the proof system P proves efficiently that learning algorithm L works, but the learning algorithm doesn't find a small circuit on the function f, then the proof system P proves efficiently that function f is hard. And when does it happen that the learning algorithm fails? Well, we know that if the function f is hard for sub-exponential size circuits, then the learning algorithm will definitely fail to find a small circuit for the function f, because the learning algorithm is small itself. So you see here where this strange notion of automatability comes from. If I used more efficient learning algorithm, I could almost close this gap between these two formulas. The important thing here is that assuming that the proof system P proves efficiently that learning is possible, we can derive not only that P is automatable, but we can conclude also that P proves efficiently that P is automatable. And this is what allows us to derive the opposite implication as well, because we can now formalize the theorem of Rasberov, Krajicek, Karmazinin, Palica, Kamez, and Kolokolova in the proof system P and conclude the opposite implication as well. This is not entirely straightforward, but with the heavy usage of bounded arithmetic, it can be done. And this is essentially how we prove the theorem. I would like to mention one more corollary. So this is an unconditional statement, which is more like an artifact of the proof methods which we used. This is the bottom box. And it says that if ZFC proves efficiently that ZFC is automatable and ZFC proves all tautologies efficiently, then you can prove the same statement inside extended Frege already. So assuming that this statement is provable in ZFC, you can prove the same thing in extended Frege. Finally, some open problems. First question, can you get rid of the main assumption of our theorem and prove unconditionally that learning and automatability is equivalent? I guess that the best way how to approach this question is just to prove some explicit circuit lower bound, finally. But eventually we hope that this can be done, right? Second, so our results show how to establish a connection between central concepts of complexity theory in the context of metamathematics, a connection which we do not know how to establish otherwise. Is it possible to resolve other questions in complexity theory in this setting? For example, can we show that learning and cryptography are equivalent? This would be very exciting, but the methods which are used in our proofs do not seem to be very useful in this case. Next, how substantial is this restriction of automatability to circuit lower bound tautologies? Is it possible that if you have automatability on circuit lower bound tautologies, then you can automate your proof system on all tautologies? This question is closely related to the question of NP completeness of MCSP. And finally, I mentioned this proof complexity collapse. If you read it counterpositively, this says that lower bound for a weak proof system can be magnified to lower bound for much stronger system. And by now we have a lot of theorems of this kind in circuit complexity. It would be nice to develop a similar theory in proof complexity, as there is some chance that it could help us to prove stronger lower bounds. All right, thank you.
Questions for you?
Is there a formal, point 3, is there already a formal relationship known between hardness for MCSP and that question? Or is it just
No,
like
this was
clearly-
just informal thing.
But it's clearly thematically related, right? Because it's like saying if I can reduce other tautologies to these circuit lower bound tautologies, that's like reducing other problems to the MCSP problem, which is like the
Yeah, this is
co-MCSP.
Yeah, this is exactly the intuition. So we expect that if you can formalize the proof of NP completeness of MCSP, then you can probably reduce automatability of the respective system on all tautologies into automatability on circuit lower bound tautologies.
Is there a question from the chat?
Yeah, I think you meant the failure of proof 2. Yeah.
Yeah, I guess this is not a question, right? Oh, I see. Oh, there is a question.
I guess there is a typo. It should be failure of crypto in point 2.
Yeah.
Yeah, learning is equal to failure of crypto. Okay, so let's thank Jan again.